Hi everybody, welcome back to the channel. In this video we're going to take a look at indefinite integrals and along with some definite integrals as well. And so we're going to talk about kind of the difference and what do you need to keep in mind. So in this section there are a lot of different types of integrals that you should keep in mind and actually I would say memorize. Just like how when you talked about derivatives and you had to memorize how to deal with the derivative using a power rule, or the derivative of exponentials, or the derivative of trig functions. It's really similar in here, where you need to be able to know how to handle an integral, and now you should be thinking integral meaning antiderivative. How do you handle an integral or an antiderivative of a constant function, of a power rule, of a trig function, of an exponential, of a logarithmic? So you got to be able to work backwards in a lot of different problems. And so we're going to see a few different examples in this video. But before we look at some examples, I want to just point out the difference between an indefinite integral and a definite integral. So let's take a look at something like this. Let's say we have the indefinite integral of f of x dx, and compare that to the integral from a to b of f of x dx. So one integral has bounds and the other one doesn't. And I want you to think about what your answer is going to look like, because it's really good after you work through a problem to be able to say, does my answer look like what it's supposed to? And where does that leave me? So when you take an indefinite integral, indefinite means there's no bounds on this. There's no a and b as a lower bound and an upper bound. So an indefinite integral, what that is going to look like is some function that we could call capital letter F. Another way to think about little letter f is that that's capital letter F prime. But you're going to get a new function, and then it's going to have a plus c on the end of it every single time. Because as we've seen before, when you take an antiderivative, we're thinking about working backwards, and when you take the derivative of something that is a constant on the end, you just get a plus 0. So any function, when you take the antiderivative, it could have had a constant on there, and we just wouldn't have known about it. But if we look at a definite integral, what we saw in the last section, definite, when we saw in the fundamental theorem of calculus, says that this is a lot like doing the antiderivative and then plugging in b and a and subtracting. So here, this is actually what the second part of the fundamental theorem of calculus says. So if you think about what f of b minus f of a looks like, this is a function where you're plugging in a value of b that's a constant and plugging a value of a that's a constant. This is just going to give you some number as a result because you're subtracting two numbers. So it's really good to keep in mind, what should your answer look like. When you're doing an indefinite integral up here, your answer should look like a new function with a constant of integration on the end. Now I will say, we also saw some problems where you can solve for what c is based on using an initial condition. So you only have this plus c on here if you're talking about an indefinite integral with no initial condition. If you have an initial condition, you still get a new function, and but you could go find what c is. However, in a definite integral like this, you're going to get a number as an answer down here. And so you're not going to get a new function because you have a number minus another number. So it is just really important to keep this in mind, because when we look at a couple of examples here, we're going to see one with an indefinite integral and one with a definite integral. We got to ask ourselves a question like, does our answer look like what it's supposed to? Does it look like a new function, or does it look like a number? Okay, so let's go ahead and jump in and look at a couple examples here. For the first one, we're going to start out with something like the integral of 1 over x squared dx. And again, you should be thinking about what kind of an integral this is. This is an indefinite integral, so our answer should look like a new function that probably has a plus c on it, since we don't have any initial conditions here. Okay, so you should think back into your kind of repertoire of derivatives and therefore antiderivatives about how to undo the derivative of 1 over x squared, or kind of what this would look like. And so you could either write it like this, or you could write it as x to the negative 2 on the inside, And if it was 1 over just an x, not an x squared, then we should be using a natural log of the absolute value of x to get to find the antiderivative. But since it's actually a -2 as the exponent, you can use a power rule here. And so for a power rule, just in general, a way to think about something like the integral of x to the n dx, we've actually seen this back when we looked at antiderivatives, is that you can do this with, let's see, it becomes 1 over n plus 1 out front, and then times x to the n plus 1. And so you can kind of work with it like here, but remember you're going back up as far as taking an antiderivative. So this should be x to the -1 power, because that's what it looks like to add 1. And then what do you need out front that's going to cancel out that -1 dropping down? Well, you need a -1 there. And then don't forget that since this is an indefinite integral, you also need to have a plus c on the end there. Or another way to write that is -1 over x plus c. Either way. Alright, so again, that shouldn't be a problem as far as thinking about an antiderivative of a power rule, I hope. Let's look at another indefinite integral here before we move on to a definite integral. And so we have something like this. The indefinite integral of 10x to the 4th minus 2 secant squared of x dx. And again, since this is an indefinite integral, we should be thinking about getting a new function as a result that has a plus c on the end. There's no bounds here, so we're not going to just end up with one number. Okay, so we can actually take the antiderivative or the integral of each of these two terms separately. Hopefully those aren't a problem, but they are different types of terms here. So for the first one, we should have a 10 out front. Let's see, it's going to be an x to the 5th power when we go back up by 1. And then we need a fraction out front that's going to cancel out that 5 moving down front. And this is trying to be consistent with the notation that I've used in other videos as well. And then after that, you can kind of combine things together out front. 10 divided by 5 is 2, so this becomes 2x to the 5th. Now what about the 2 secant squared of x? Okay, hopefully pretty clearly that is a -2. You just leave that -2 out front. And then the antiderivative of a secant squared of x is actually the tangent of x. Okay, so we don't really need to do much with that. That's about the best we can do. But remember, I keep mentioning this over and over again, this is kind of the point of this video, is to remember that when you take an indefinite integral here, you should be having a plus c on the end. So plus c. Okay, so now let's look at an example of a definite integral. And after you do some of these, I think what you'll find is that definite integrals actually tend to take a little bit more work or a little bit more time, because you're not just finding the antiderivative, you're also plugging in a value, and that can take you a little bit longer. It can take you a couple other steps. So let's take a look at something that looks like this. 2x to the 3rd minus 6x plus 3 over x squared plus 1. Okay, always need that dx on the end. And first, before we worry about the a and the b, the lower bound and the upper bound there, we first need to start out by finding the antiderivative. So that's going to be something like 2, let's see, we're going to have an x to the 4th power when you add 1, and then have a fraction out front that would undo the 4 dropping down. We leave the 6 out front, it's going to be an x to the 2nd power. So we need a 1/2, and so we could simplify both of those. This becomes a 1/2 x to the 4th minus 3x squared. Now we just got to deal with that last term over here. And I'll remind you that another way to write that is to write it as 3 times 1 over x squared plus 1. That's before you actually take the antiderivative. The 1 over x squared plus 1 is a little bit less commonly remembered, but it's a good one for you to think back to. It involves trig functions as well, but specifically it involves inverse trig functions. So a little bit less commonly remembered, but a good one to look back and to kind of put in your memory bank or or have in front of you as a big list of derivatives and antiderivatives, this one looks like 3 times the arctangent, or the inverse tangent, of x. And then also don't forget our plus c. And again, just like last time, we can't really do much to simplify that, so we'll just leave it as 3 times the arctangent of x plus c. Now here's the difference, is that this is a definite integral. So I guess with the definite integral, we actually didn't even need to write this plus c in here, because what we're going to see is that when we have b and a and we plug those in, we're going to have, like, it's going to be like having a plus c and then a minus c. They're going to cancel each other out. So here's the notation we often use. We'll often use this notation here on the end that says start at x equals 2, or start at x equals 0 and end at x equals 2. And so we put this kind of vertical bar up here that says plug in 2, plug in 0, and then subtract. So that's just a good way to kind of remember what that notation looks like. And we would then go ahead and just plug that in, and so we'd have 1/2 times 2 to the 4th minus 3 times 2 squared plus 3 times the inverse tangent of 2. There's our f of 2, and then be careful with this. This is a really big thing we want to be careful about here, is that it should look like minus f of 0. F of 0 is that whole thing in parentheses, so just be really careful there, that it's not just that don't be careful that you're not forgetting the parentheses there, because those are really important. We need to subtract that whole thing. So we get something like this, and then plus 3 times the inverse tangent of 0. Okay, so you could go ahead and figure out what all of this is together, or grab your calculator here and evaluate all of this, and that's what we would get as our answer. The fact that we have a 0 in here actually makes things pretty nice, though, because this is 0, 3 times 0 squared is 0, and actually the inverse tangent of 0 is actually also 0. The tangent of 0 is equal to 0, meaning the tangent function goes through the origin, so that's kind of nice because this whole thing is just minus 0 on the end. So let's see, 2 to the 4th is 16, and then divided by 2 you get 8 here, and then this is minus 3 times 4 is 12, and then plus 3 times the inverse tangent of 2, which is not going to be a very friendly number. So if we're trying to write this as an exact value, we could either write it as negative 4 plus 3 times the inverse tangent of 2, or you could find what that is as a decimal, and that's probably okay depending on the question that you're being asked. You can decide whether you want to use exact numbers or whether decimals are okay. But the main idea here that you want to be careful about, I hope what you're hearing in this video, is that you want to be really careful about whether the integral you have is a definite integral, where you should be getting one number as your answer, or whether you have an indefinite integral, where your answer should look like a new function, probably with a plus c on the end, unless you have an initial condition. Okay, hope you've enjoyed the video.